Let's start with an introduction to quadratic equations. A quadratic equation is a second-degree equation which will be written in the form ax squared plus bx plus c equals 0, where x is our variable, and a, b, and c are coefficients and constants. When we solve an equation like this, we're looking for all values of x or all values of the variable that will make the equation true. The name for these solutions is the roots of the equation. So before we start solving them, we're just going to look at the theory behind this and introduce a little bit of vocabulary. There are a few equivalents we can look at. So when we talk about an equation, we talk about something with an equal sign. We can associate this quadratic equation with an expression or a polynomial without an equal sign. I'm going to label this one expression. We can also connect it to a function written in function notation, or a graph written in the form y equals. We're actually going to start by looking at the graph just to get the idea of the theory behind this. So when we solve, what we're going to do is we're going to find the related graph, and we're going to look for the places where y is equal to 0, which is essentially just our x-intercepts. So going over the different ways you may be asked to find this, when we talk about an equation and solving, we call those the roots of the equation. When we look at a graph, we look for the x-intercepts of the graph, which is the places where y is equal to 0. When we write it in function notation, we also call these zeros, the x values that will make the function equal to 0. Let's take a look. So here we have a given example of an equation and the related graph. So for this graph here, this is the graph x squared minus 6x plus 5. This allows us to solve the related equation where x squared minus 6x plus 5 is equal to 0. We do this by looking for the x values that will make y equal to 0, and we can see they're indicated on the graph. One here and one here. These are also our x-intercepts. We can solve by graphing and then identifying the x-intercepts if we can read them nicely off the graph. We can also solve algebraically. And the way I would do this for an equation like this is I would factor it. So for example, if we have 0 equals x squared minus 6x plus 5, we're used to solving that by putting it in a factored form instead. So we look for two numbers that multiply to positive 5, but add to negative 6, and our factors are x minus 5 times x minus 1. We've done a little bit of solving like this, where we look at each of the factors in turn, and we say that either the first factor must be equal to 0 or the second factor must be equal to 0. If x minus 5 is equal to 0, we know that x is equal to 5. That identifies one x-intercept. If x minus 1 is equal to 0, we know that x is equal to 1. That identifies our other x-intercept. So this is kind of the relationship between the graph and the equation. If you are given a graph, you can use that to identify any possible solutions, or also just the number of solutions or roots. So when we're asked how many unique real roots does each graph have, we're essentially saying how many x-intercepts, and we can just read that off the graph. This first graph has 2. The second graph only has one unique real root, and the third one does not have any x-intercepts and therefore no solutions or no roots. From here, we can start to look at solving algebraically.